The F-35 Lightning II, a masterclass in aerospace engineering. Aviation has always been defined by the relentless pursuit of the next frontier. From the fabric and wood of the early 20th century to the supersonic aluminum structures of the Cold War, aerospace engineering has consistently pushed the boundaries of what is physically possible. Today, we stand at the pinnacle of this century-long evolution. Before us is the F-35 Lightning II. To call it an aircraft is mathematically accurate, yet fundamentally incomplete. It is, more accurately, a highly advanced integrated flying data center. It represents a paradigm shift in aviation design, moving away from pure kinematic performance, how fast an aircraft can fly or how tightly it can turn, and toward information dominance, sensor integration, and low observable technology. In this comprehensive engineering analysis, we will deconstruct the F-35. We will look past the composite skin and delve into the complex mechanics, thermodynamics, and software architectures that make this machine operate. We will explore how thousands of individual components, from the articulating titanium fan blades to the microscopic layers of radar-absorbent materials, operate in perfect synchronization. This is not a story of hardware alone. It is a story of unprecedented computational power, advanced fluid dynamics, and a unified design philosophy that has resulted in the most complex aerospace platform ever realized. Welcome to the architecture of modern flight. Development history. The genesis of the F-35 lies in a procurement initiative known as the Joint Strike Fighter, or JSF program, initiated in the 1990s. The engineering challenge presented to the aerospace industry was unprecedented in its scope. The objective was not simply to build a new aircraft, but to engineer a single baseline platform that could satisfy the distinct operational requirements of three different operational branches. Historically, aircraft were highly specialized. An airframe designed for conventional runways was fundamentally different from one designed to endure the extreme mechanical stresses of aircraft carrier launches, which in turn was entirely different from an aircraft capable of hovering like a helicopter. The JSF program demanded all three capabilities from a single core design. This requirement led to the development of three distinct variants: the F-35A, designed for conventional takeoff and landing, the F-35B, engineered for short takeoff and vertical landing, and the F-35C, optimized for carrier-based operations with larger wing surfaces and reinforced landing gear. To achieve this, engineers utilized advanced computer-aided design to create a modular airframe. This meant the central fuselage, the cockpit, and the primary avionics systems remained largely identical across all variants, while the propulsion integration and lifting surfaces were adapted. During the competitive phase, two distinct design philosophies emerged: the X-32 and the X-35. The X-35 ultimately demonstrated a more stable approach to the vertical landing requirement through an innovative shaft-driven lift fan concept, a mechanical marvel we will explore in detail later. The transition from the X-35 prototype to the final production F-35 required years of rigorous refinement, transforming a proof of concept into a reliable, integrated, and highly sophisticated aerospace vehicle. Aerodynamic design. The physical shape of the F-35 is a masterclass in aerodynamic compromise. In aerospace engineering, every curve and angle is a negotiation between lift, drag, and stealth. Unlike older generations of aircraft, which often featured external payload stations and auxiliary fuel tanks, the F-35 relies heavily on a blended wing body design. The fuselage transitions seamlessly into the wings, creating a continuous aerodynamic surface. This not only increases internal volume for fuel and operational equipment, but also significantly reduces aerodynamic drag. Notice the nose of the aircraft. It features a distinct horizontal ridge known as a chine. In flight, particularly at high angles of attack, these chines generate powerful vortexes, spiraling tubes of low-pressure air. These vortexes travel aft over the wings, re-energizing the boundary layer and providing the aircraft with remarkable stability and lift at low speeds, preventing aerodynamic stalls. The internal storage bays are a critical aerodynamic feature. By carrying equipment internally rather than on the wings, the F-35 maintains an exceptionally clean aerodynamic profile. This pristine shape ensures that the airflow remains largely laminar or smooth over the skin of the aircraft. The control surfaces, the ailerons, horizontal stabilizers, and the twin outward-canted vertical tails are entirely governed by a complex fly-by-wire system. The pilot does not mechanically move these surfaces. Instead, the pilot inputs a desired trajectory, and the flight control computers calculate exactly how many degrees each surface must deflect to achieve that maneuver, compensating for airspeed, altitude, and air density in milliseconds. The canted tails specifically provide immense directional stability while contributing to the aircraft's overall low observable shaping.
Stealth technology. Perhaps the most discussed yet least understood aspect of the F-35 is its low observable or stealth technology. Stealth is not invisibility. It is the science of delaying detection by manipulating the electromagnetic spectrum. Radar systems operate by emitting electromagnetic waves and measuring the reflections that bounce back from an object. The larger the reflection, the larger the radar cross-section, or RCS. The engineering goal of the F-35 is to minimize this RCS to the size of a very small bird or an insect. This is achieved through two primary engineering principles: shape and materials. First, consider the shape. The entire airframe is designed using a principle called continuous curvature and edge alignment. If you draw a line along the leading edge of the right wing, you will find it is perfectly parallel to the trailing edge of the left wing. The access panels, the landing gear doors, and even the internal equipment bay doors feature serrated, zigzag edges. These angles are precisely calculated to reflect incoming radar waves away from the receiver, rather than bouncing them directly back. Second, we examine the materials. The skin of the F-35 is manufactured from advanced composite structures and coated with radar-absorbent material, or RAM. While the exact chemical composition remains highly classified, the physics behind it is clear. RAM contains microscopic particles, often carbon or iron-based, suspended in a dielectric matrix. When a radar wave penetrates this coating, the electromagnetic energy oscillates the particles. This friction converts the electromagnetic energy into a minute amount of thermal energy, effectively absorbing the radar wave. However, stealth also requires thermal management. Jet engines produce immense heat. To reduce its infrared signature, the F-35 employs a highly advanced thermal management system. Fuel acts as a primary heat sink. Before it is burned in the engine, the cold aviation fuel is cycled through heat exchangers to cool the aircraft's powerful avionics and sensors, while the engine exhaust nozzle is designed to mix bypass air with the hot exhaust, rapidly dissipating the thermal plume into the atmosphere.
Engine and power system. The heartbeat of the F-35 is the Pratt & Whitney F-135 turbofan engine. It is recognized as one of the most powerful fighter engines ever produced, capable of generating over 40,000 pounds of thrust. The F-135 is a low-bypass turbofan. air enters through the two bifurcated intakes, which use a diverterless supersonic inlet design to strip away turbulent boundary layer air, and is compressed through multiple stages of titanium fan blades. In the combustion chamber, this highly compressed air is mixed with fuel and ignited. The expanding gases rush backward, turning the turbine section, which in turn powers the front compressor, before being expelled through the rear nozzle. The materials inside the high-pressure turbine operate in an environment where temperatures far exceed the melting point of the metals themselves. Engineers solved this thermodynamic paradox by growing single-crystal turbine blades and using complex internal cooling channels, allowing microscopic films of cooler air to protect the metal from the superheated gas. The most spectacular mechanical achievement in the F-35 family belongs to the STOVL variant, the F-35B. To achieve vertical flight, the engine utilizes a patented 3-bearing swivel module. The rear exhaust nozzle can articulate downwards in just 90 degrees in seconds. Simultaneously, a complex mechanical clutch engages, connecting a drive shaft from the main engine to a massive lift fan located directly behind the cockpit. This lift fan, featuring counter-rotating blades, pulls cold air from above the aircraft and forces it downward, providing a massive pillar of thrust. Together with small roll post thrusters under the wings for lateral stability, the F-35B achieves a perfect balance, allowing a multi-ton machine to hover motionless in the sky.
Sensor systems. If the engine is the heart of the F-35, its sensor suite is its nervous system. This aircraft is designed to gather, process, and distribute an unprecedented volume of data regarding its surrounding environment. The primary active sensor is the AN/APG-81 Active Electronically Scanned Array, or AESA, radar. Older radar systems used a single large dish that mechanically tilted and panned. An AESA radar, by contrast, contains over 1,000 individual solid-state transmit and receive modules. By subtly shifting the timing of the electronic signals sent to these modules, the radar beam can be steered instantaneously in any direction without any moving parts. This allows the F-35 to scan the airspace, map the ground, and track multiple targets simultaneously with incredible precision and minimal energy emission. Beneath the nose is the Electro-Optical Targeting System, or EOTS. Housed behind geometric, faceted sapphire glass, this system provides high-resolution, long-range infrared and optical imaging. But the true innovation is the Distributed Aperture System, or DAS. 6 high-resolution infrared cameras are seamlessly integrated into the skin of the aircraft, providing a continuous 360-degree spherical view of the environment. The DAS operates autonomously, constantly monitoring for thermal anomalies, tracking other aircraft, and providing navigational visual data. The brilliance of the F-35 lies in sensor fusion. In older aircraft, a pilot had to look at a radar screen, a separate infrared screen, and a separate data link screen, mentally combining the information. The F-35's central computers do this heavy lifting. They ingest the data from the AESA radar, the EOTS, the DAS, and external data feeds and fuse them into a single, cohesive, highly intuitive graphical interface.
Cockpit and pilot interface. The interface between the human operator and this immensely complex machine is a marvel of ergonomic and software design. Upon entering the F-35 cockpit, the first thing one notices is the absence of traditional dials, gauges, or physical switches. The entire instrument panel has been replaced by the panoramic cockpit display. This is a single large piece of continuous glass featuring full touchscreen capabilities.
The pilot can customize this digital workspace, organizing the layout of navigation maps, sensor feeds, and system diagnostics with the swipe of a gloved finger, much like operating a tablet computer. However, the most critical piece of interface technology is worn by the pilot. The F-35 does not feature a traditional head-up display mounted on the dashboard. Instead, all critical flight data, airspeed, heading, altitude, and targeting information is projected directly onto the visor of the Generation 3 helmet-mounted display system. Because this helmet is integrated with the aircraft's DAS cameras, an extraordinary capability is unlocked. If the pilot looks down at their feet, the helmet displays the camera feed from the belly of the aircraft. The pilot can essentially see right through the solid structure of the airframe, gaining unimpeded situational awareness in every direction. The helmet is custom-fitted to the precise biometric measurements of each individual pilot's head to ensure the optical projections align perfectly with their pupils.
Software and data systems. The F-35 is fundamentally a software-defined aircraft. The physical hardware is largely a conduit for the millions of lines of sophisticated code that govern every aspect of its operation. To put this in perspective, the flight control and mission systems rely on over 8 million lines of software code, significantly more than any previous aerospace platform. This immense computational capability allows the aircraft to operate as an advanced network node. Through secure, high-bandwidth data links, an F-35 can silently share its fused sensor picture with other aircraft, naval vessels, and ground-based control centers. It acts as an airborne quarterback, analyzing the environment and distributing critical information to allied platforms, enhancing the situational awareness of the entire network. Furthermore, software governs the aircraft's maintenance and life cycle through systems like ALIS, the Autonomic Logistics Information System, which is currently transitioning to the cloud-based Odin network. The aircraft constantly monitors the health of its own components. If a specific valve or sensor is showing signs of degradation, the aircraft software will log the anomaly, automatically transmit a diagnostic report to the ground crew, and even check the global supply chain for a replacement part before the aircraft has even landed. This predictive maintenance is a revolution in operational efficiency.
Comparison with other aircraft. To fully appreciate the engineering of the F-35, it is instructive to compare its design philosophy with other contemporary aerospace platforms. Consider the F-22 Raptor. Designed primarily for extreme high-altitude performance and high-speed maneuverability, the F-22 relies on raw kinetic energy and thrust vectoring modules for physical dominance. The F-35, by contrast, is optimized for multi-role versatility and information superiority. While highly maneuverable, the F-35's priority is not pure speed, but rather maintaining a low radar signature while processing vast amounts of environmental data. When comparing the F-35 to advanced delta-wing platforms like the Eurofighter Typhoon, the engineering divergences are clear. The Typhoon utilizes a canard delta configuration to achieve incredible aerodynamic agility and climb rates. However, it features external payload stations and a higher radar cross-section. The F-35 sacrifices some of that absolute aerodynamic agility in favor of strict internal carriage and stealth shaping, relying on its sensors to identify variables before it is ever detected. Similarly, compared to platforms like the S-570, which features heavy emphasis on thrust vectoring and mechanical maneuverability, the F-35 relies entirely on its sensor fusion and secure networking capabilities. The engineering consensus of the F-35 program is that modern aerospace operations are decided by computing power and data integration, rendering mechanical dogfighting metrics secondary to electronic and informational supremacy.
The F-35 Lightning II is far more than a collection of advanced materials and powerful engines. It represents a fundamental evolution in how we conceive of aerospace engineering. It is the realization of decades of research into fluid dynamics, electromagnetics, thermodynamics, and computer science, fused into a single, cohesive platform. By prioritizing stealth, sensor integration, and software architecture over traditional kinetic metrics, engineers have created a system that perceives the environment with unparalleled clarity. The challenges involved in its development were staggering, requiring the aerospace industry to invent new manufacturing techniques, write millions of lines of code, and push the boundaries of material science. The result is an aircraft that operates not just within the physical atmosphere, but within the complex digital networks of modern operational environments. As we look toward the future of aviation, the architecture of the F-35 will serve as the foundation for the next generation of flight. It stands as a profound testament to human ingenuity, a seamless integration of human intelligence and machine capability, flying silently at the edge of the stratosphere.